Yes. So please state this. Okay. Thank you. Okay. Hi everyone. I'm Wang Dongxu from Nuremberg University, China. Today my topic is on water leak phenomena in simulation of floating body using OVERSET grid. My presentation consists of 5 parts. The first is background. We all know that OVERSET grid is a deformation method in terms of simulating floating structures, especially with big motion, because the grid quality can remain good during the simulation. Here is a typical OVERSET grid. It may consist of at least 2 parts, a background grid and a structure grid. So these 2 grids exchange information through mass interpolation. That's a reason for the mass non-conservation problem of the OVERSET grid. To overcome this problem, one may improve interpolation accuracy or just enforce the conservation at the interface. And here we will focus the former. In a previous study, we have made these attempts to improve the performance of the OVERSET grid. The first attempt we have made is to use different mesh interpolation schemes. We first developed a canal interpolation scheme according to SPH models, and we also implemented the polynomial scheme proposed by China to our numerical model. The second attempt we made is to extend donor cell stencil, that is to find more donors for a given interpolated cell. The third attempt we made is to ensure strong coupling between motion and flow field. To achieve this, in FV solution, we modified the outer loop number to 5 and the second parameter to yes. In addition, we use the extended ABM to update the structure motion. By simulating a case of a 2-dimensional static floating box there, we found the following conclusions. The first is the canal scheme makes a better trade-off between the accuracy and efficiency. The second is that the polynomial scheme is highly unstable near interface because the weight is unbounded between 0 and 1. It was solved. The third conclusion is that extending donor cell stencils is not effective in improving the performance of the OVERSET grid. In fact, it has a negative effect. Then the fourth is ensuring strong coupling between structure motion and the flow field helps the block stay still. So based on this result, we may obtain the motivation of the present study here we talk about. That is to answer the following 3 questions. First, is it still the case for 3-dimensional simulations, especially for rotational motions? The second is there a method to stabilize the polynomial scheme in 2-phase flow? The third is for 3-dimensional simulations, is an increase in construction time affordable? The second part is numerical method. Because we only have 15 minutes, so we will just give a short introduction of the numerical method. The first is governing equations. We have mass conservation and momentum conservation equations. We also have VOF equations. We use the isolated vector proposed by Mr. Rumby, and an artificial source is added to the right hand of the equation to eliminate the air bubbles in backward region. And the second part is the bounded value least square corrected polynomial scheme. This is an iterative algorithm to ensure the solution of over-determined linear system is in a range from the lower bound to the upper bound. So by doing so, the keywords in every scheme may become like this. We have a lower bound. Here we use ye minus 5 and the upper bound 1. Then it's the third part simulation case. We first simulate a 3-dimensional static floating box case. Here's some details of the case. And the right 2 table lists some critical numerical size, as well as the cell size and cell number. Note that all the cases were run in parallel mode with 8 processors. The first part is result analysis. First is The left figure shows the effect of spatial and the temporal resolution, and the top sub-figure is the variation of the total water volume. The bottom sub-figure is a Hill motion signal. Here, C, M, and R represent the torus, medium, and refined mesh, and the number behind is the maximum prime number we used. And the MD is short for mesh deformation method. So, from the left figure, we may see that in all the cases here, the box cannot stay still, and the water leak phenomenon appears when the overset grid is used. The right figure displays the effect of interpolation scheme and coupling strategy. Here, W and F represent weak and strong coupling. It is clear that once the strong coupling strategy is used, the water leak phenomenon disappears and the box can stay still. But the result of the pitch case is not as good as that of the Hill case. We can see that the effect of spatial and temporal resolution, as well as the interpolation scheme and the coupling strategy, is not as significant as we expected. The total water volume will first increase by nearly 1% and then start to decrease. The mesh deformation method failed to simulate such a case because the grid quality became so poor. Then we conduct a quantitative analysis on our simulation results. We introduced the two parameters, the water volume variation and water volume variation amplitude, P1 and P2. The table listed all the values of the two parameters from lines. We see that for the Hill case, once the strong coupling strategy is used, the performance of the OVERSET grid in terms of mass conservation is very close to that of the mesh deformation method. But for the pitch case, we failed to obtain any definite conclusion. But the only observation may be the fact that the mean value for all the cases for P1 and P2 is smaller than that of the Hill case. Then it's a quantitative analysis of computational time. The figure displays the effect of the maximum prime number, grid density, and the interpolation scheme on the effect of on the computation time. Here, the grid density is defined as the weighted cell number surrounding a floating box. And note that we have treated the computational time of case number 2 as the reference time. So from this figure, we may obtain 3 conclusions. The first is from the top 2 sub-figure, is that decreasing the maximum prime number by a factor of 2 or increasing grid density by a factor of 1.2 to 1.3 doubles the computational time. The second conclusion is replacing the cell volume weighted scheme by the canal or polynomial scheme reduces the computational time by a factor of 0.5 or 0.8 for the Hill case. But it increased the computational time by a factor of 1.05 or 1.23 for the pitch case. Note that this is under the condition of weak coupling. And the third conclusion is changing the outer loop number from 1 to 5 does not increase the computational time significantly for the Hill case because the water leak phenomenon has almost disappeared. And but it indeed increased the computational time for the pitch case. However, the above conclusions were obtained based on the case of a static box, which is seldom seen in our real simulation. So we made a double check on the of these conclusions by simulating a similar 3-dimensional floating box case. In this case, a reservoir is added to a corner of the computational domain, and the box is allowed to conduct hill and pitch motion. We confirm that the result is somehow lacks that of the Hill case. the water leak phenomenon still appears, and using a higher temporal and spatial resolution helps to improve the result of the OVERSET grade. However, the use of strong coupling strategy cannot eliminate the water leak phenomenon. From the above results, we may deduce that the reason is the rotational motion of the floating box. Then it's a consistency result, and we also treated the computational time of case number 2 as a reference. And based on this consistency result, we may do some small modification on the previous 3 conclusions. So the first conclusion is okay, and the second may become replacing the cell volume weighting scheme by the canal or polynomial scheme reduces the simulation time by a factor of 0.64 or 0.73. This is under condition of recoupling. And the third conclusion may be modified as changing the outer loop number from 1 to 5 increase the simulation time by a factor of 3. So finally, we can obtain our conclusion. That is to answer the 3 questions we have mentioned. The first is that the canal scheme still make a better trade-off between accuracy and efficiency for 3-dimensional simulation, especially for rotational motion. So the answer is yes. Under the condition of recoupling compared to using the cell volume weight scheme, using the canal scheme reduces the computation time by nearly 30 or 35%, and the accuracy improves slightly. The second question is that is there a method to stabilize the polynomial scheme in 2-phase flow simulation? The answer is still yes. The introduction of this bounded value least square correction to stabilize the polynomial scheme. However, because the weight is bounded, the accuracy of the polynomial scheme may decrease slightly. The third question is that for 3-dimensional simulations, there's an increase in computation time affordable. To be honest, it's hard to say. If the mesh interpolation scheme is unchanged, changing the outer loop number from 1 to 5 increases the simulation time by a factor of 4.5, which means the outer loop number and the computation time may have a linear relationship. But if the mesh interpolation scheme changes from the cell volume weight to canal or polynomial, changing the outer loop number from 1 to 5 increase the computation time by a factor of 3. So in general, to evaluate the water leak phenomenon, the canal scheme is recommended, and the strong coupling strategies are recommended as well. When the temporal, especially when the temporal and spatial resolution is not sufficiently high, such as maximum prime number equals 0.5 and the gradient density equals 12, which was used in our simulation. That's all. And here may be some useful information. This is the numerical sightings we used, and this is the open source program I developed by me. And this was open source. And currently, only a beta version is available, and users are mostly Chinese. And this is for the numerical modeling in the field of coastal or oceanic engineering. And I will continue to develop this toolbox for the communication or cooperation. Welcome. Thank you for listening.
That's why you're looking for presentation. It's very curious you are working with that. It's huge. I just want to make sure that I understand the reading of because in my mind it's always been something about having one fraction field. You have it on the one base, and you have it on the other one, but you need to interpolate in times on the basis. And if you just interpolate using whichever scheme then that will not guarantee conciliation of the water on right?
Yeah.
And I don't understand how can this fall, how can we have the concept. So my what the problem does is it does something about how motion of the body is, but in principle, even if you have frontal motion, like prescribed motion, deep motion, you still have that problem with integration between the two mesh. And so I don't understand why our operators can help. Do you have any sort of understanding?
Okay. So you mean this figure?
Yeah, I don't understand why they want to try to use our operators. I think I would just try to describe the motion case and then look at that to sort of get away with all that operator stuff. Maybe I misunderstood it.
Okay. So in my opinion, the water leak phenomenon may consist of two stages. The first is the move of the static box. Because I think it's because I'm solving some problem in the solving procedure. I'm not sure, but the start of the motion of the box may be the start of the water leak phenomenon. And the use of strong coupling, I think, because the velocity matrix is updated in each outer loop. I mean, so the problem in the solving process may be alleviated, and the box can stay still. And then because the start of the case, the two grids are completely overlapping each other, so it may help to alleviate the water leak phenomenon. That's my opinion. And then, but as you say, for some prescribed motion or something, I think in our case, and we still need to, as mentioned, use higher order interpretation schemes to just ensure enforce confirmation interface by using some flash corrected method or something, but it is very time consuming. So we focus on improving the interpretation accuracy here. But to be honest, yeah, the fundamental problem still exists. Yeah. But indeed, using a high order interpretation scheme helps to improve the performance of the OVERSET grid. Yeah. Thank you.
Yes,
okay. Version? Oh no. Okay. I will ask the first question. The version of OpenFOAM, you mean? Yeah. I think the version is not critical, but I use 2006. But as far as I know, the OVERSET grid, the source code is not modified since the 1806, maybe. So, yeah, I think
generations ago, there was an improvement on OVERSET integration. I mean, you have to have an improvement with reduce the level of vehicle or you are using version.
you mean just
It's a cool question. You see the previous videos where there are ways for a hybrid.
I believe it's yes, but the critical problem here is the computation, the size of the computation domain and the overlap region. So the mass non-conservation problem may appear in the overlap region, but you can see that the small computational domain, and the waves on current or wind contained, we may have a long computational domain. So this problem may be not as significant as we have obtained, but the problem still exists, I think.
Okay,
Is it
here we
working?
go.
Oh, okay.
We see you. We see your presentation. Please put the full screen and we hear you.
Okay, perfect. So thank you very much for this introduction. My name is Gabriel Barajas, and today I'm going to present my work, which is entitled Simulation Period Damping Forces using the POROUS mediums applied to coastal and offshore engineering. So this is going to be today's the index of my presentation. I will first start describing IH Cartabra, which is a research institute I've been working for the last 15 years. Then I will explain briefly our new POROUS solver, the version 2.0 of OpenFOAM, applied to medium solvers, POROUS medium solvers. And then I will show two applications. The first one is applied to coastal engineering, which is the analysis of the PDO damping force on a dual chamber oscillator water column. And the second one is an application to offshore engineering, which is the PDO damping of a floating wave energy converter, WEC. So I work for IH Cantabria, which is the Environmental Hydraulics Institute, which is a research center specialized in basic and applied research, and is located in Santander in the north of Spain. We are around, more or less now, around 200 people working in the institute. So for the last 15 years, we've been working worldwide in more than 70 countries, doing more than 1,200 projects, always related to coastal and offshore engineering. So here I'm just doing a small review of some of our partners. Here we can see the multilateral, the national, the regional, the foreigner, some research centers and universities that I've been working with for the last 15 years. And if we move into the private sector, I have divided in 6 blocks: energy, construction, engineering, consulting, environment and technology. And we can see that we have probably the main actors related to our field. So once I have introduced IH Cantabria, I will briefly explain which is our POROUS solver, the version 2.0. So when we are working with a waveflow and we don't have any POROUS medium solver inside, we are going to be solving the Navier-Stokes equations, the Rand equations, Reynolds average Navier-Stokes equations, plus a VOF equation. Through this work, we are going to be always using the Muse algorithm to solve the VOF equation. So this is implemented in the Interform standard solver. But when we are dealing with the POROUS medium, we have to add the volume average Reynolds average Navier-Stokes equations, of course, plus the VOF equation, and we have called this new solver, we have called it IHFOAM. So we are going to be using a macroscopic approach to describe the POROUS media flow in the numerical simulations, which calculates a mean behavior within the POROUS zone. The idea is to, because of the complexity and lack of information of this internal structure, to model the linear and nonlinear drag forces following the Forchheimer's formula. And for defining the Forchheimer parameters, we're going to be using the expressions by Wang 1995 for the A, the B, and the C. So if we have, for example, a waveflow, and we put inside this two-dimensional domain 2 POROUS zones. So we can see here on the first graph, on first picture, the new implementation, or the most important part of this new implementation is now that the water is going to be bounded between 0 and porosity. Of course, outside the porous median is between 0 and 1, because porosity is 1 outside of the porous media, and inside of those porous media is going to be between 0 and its own porosity. Velocity, of course, is going to be damped inside of those porous median according to the equations. And as we are going to be using the same fluid through the whole wave flume, density must be kept constant, and in this case is water. So we follow classical validations following the work by Lin 1998. Here I'm just presenting 2 of those experiments, but for each of the materials, glass beds and crushed stones has 2 different setups. So on the left, I'm confronting the experimental data, which is the black circles against our numerical results, which is the blue line. And on the right, I'm presenting, which is the one plotting the mass evolution, the total mass evolution. The dotted line is the first version of the POROUS media solver, and the new thick red line is the new version. And we can see that we have achieved mass conservation through the whole simulation. Blue is water and red is air. Of course, this implementation can work with different discretizations of in the same mesh. Here we have, for example, this discretization around the breakwater here. You want to calculate runoffs, for example. And of course, as I said before, we just validated this new numerical solver with all the 4 experiments from Lean 1998. And then what we did is we extended this work to be used the porous median solver in the OVERSET framework. We published a paper which is entitled Tsunami Generated by Submerged Landslides, Numerical Analysis of Linear Field Wave Characteristics. The main leader of this part was Alessandro Romano. I think that Alessandro is on the room today. If you can, Alessandro, raise your hand. I hope someone is raising his hands, otherwise I'm going to look a bit like a crazy man. So we extended this work now, the porous median solver, to be able to be worked with in the OVERSET framework. We know when we have some moving devices that at least we must have 4 cells between the moving or the OVERSET device and one of the boundaries. The idea was to replicate this wall by a porous median. So with a small permeability, so it didn't allow the water to go inside and it was acting like a wall. You can find this working on the website, this one. So here I'm just going to present in 2 examples of this new porous median solver application. This first one is a real breakwater we have here in the north of Spain, and we were calculating forces for a solitary that was representing like a tsunami. So this breakwater is composed of multiple different porous structures. And we were interested as well on calculating the forces on those 2 main buildings in case we have this kind of huge events. The second one is another sort of application. We are generating, in this case, our wave with our dynamic boundary condition. So the wave is going to be interacting with the bottom, and here we have 3 intake towers. So we're going to see we have this run-up event. Some of the wave is going to be reflected, some of the wave is going to be dissipated through the breakwater, and we can see even how the fluid goes through these 3 intake towers into the pipes. So once I have presented the new porous median solver, I'm going to be talking about these 2 applications. The first one is the analysis of the PTO damping force on a dual chamber oscillator water column. I'm doing this work with Jorge Gadelo from Lenec, Portugal. Jorge is the one here with the red t-shirt. So the idea is to reproduce a set of experiments with a numerical model. Of course, in this case, it's going to be OpenFOAM. So here we have our physical experiments in which we have placed our dual chamber oscillator water column in a wave flume. We have a dissipative beach, and then we can see here that we have even some bathymetry. The idea is to reproduce this with CFD and to create another methodology for a fast 3D numerical analysis of the PTO damping force on the dual chamber oscillator water column. So as we were going to try things fast, we're going to be using 3 approaches. The first approach is to model the PTO as in the experiments, as we can see here, which means that holes in the top of the chambers to reproduce geometrically the same openings used as in the experimental setup, exact geometry. The second one, we're going to model our PTO using our porous median solver, the one I have already presented, following the Forheimer equations. And the third one is to add directly a drag force in the momentum equation. Okay. So for these first cases, for the first and third approach, we're going to be using the interphone. We have no porous median solver. And for the second one, of course, we're going to be using an IH-phone system meter pair solver. Probably through the whole simulation, I think I have used the K omega SST with enhancement of Larsen and Fuhrman to reduce the overproduction of turbulent kinetic energy below the waves. Here we have tested different cases. Here I'm just going to show results from 2 of them. Something that I want to point again is that for the first approach, we are going to model exactly the experiments. So we're going to model the whole as it is in the experiments. But for the second 2 approaches, the second and the third approach, we are not going to model this whole, but we are going to add this kind of area in which we are going to be, or is going to be characterized in the second approach by a porous median porous medium following the four-Heimer equations, or in the third approach as a reduction in the momentum, adding directly in the equations a drag force. So for the first case, which has these are regular waves, so water depth of 0.384 meters, wave height of 0.075 meters, period of 2 seconds. I'm going to be plotting free surface elevation on top and air pressure below. This is for chamber 1 and for chamber 2. Through the whole work, both in this part, experimental data is going to be the black lines, and then I'm going to be plotting the first, the second, and third approach. So we can see that we have a good agreement between all of them. And what is really important is that with the second approach, we have reduced the simulations by 25%, and with the third approach by 40%. This is another of the cases, the third one. And as before, we can see that we have a good agreement between experimental and these three numerical approaches. So something that it is important, but of course, the oscillating water column behaves differently for different wave conditions as expected. Here, I'm just plotting the results for the first, the second, the third, the fourth, and the fifth cases. All of them are regular cases, and we will vary in the period of the waves. And we have checked that, or we have analyzed that the chamber 1 is more efficient for low periods, and chamber 2 is more efficient for high periods. Yeah, I'm going to put some videos. I'm going to be plotting here the surface elevation, here velocity on the air, and here velocity on the fluid flow, on the water, sorry. So as I said before, we can prove to be faster by 25% up to 40% using the second and third approach, if we compare it to the first approach, in which we reproduce the exact experimental setup. And on the other hand, because damping numerical regions cannot replicate the flow in the vicinity of the PTO, so we have velocities around here which are 10 times bigger than the experimental data. But this is normal because our geometry, our numerical geometry is completely different. The sensors that we are confronting all the time are placed around here in the middle part of the chambers. So once we did it with the compressible approach, so we thought it was nice to change it to the compressible approach. We are not just going to be using the first, which is the exact geometry, and the third approach, because we know the second one is not fast enough. Again, I'm just going to be plotting some results from some of the test cases that we have validated. Now I have added those two new lines, which is for the compressible, the holes, which is the second, and this would be the third approach. Sorry, this would be a 3 here. And we can see that we have a good agreement overall. For another case, I'm just plotting here the pressure in the first chamber and the second chamber, and we have a good agreement as well. And as before, we just added here the compressibility of the air. We are having, or we are obtaining the same results. So chamber 1 is more efficient for low periods, and chamber 2 is more efficient for high periods. Of course, now I can plot the same videos. And as we have added the compressibility, so the density changes, and we have the temperature that is going to be plotted here in green. Of course, when the air is compressed, the temperature is going to increase, and when the air is compressed inside the chamber, the temperature is going to be reduced. As before, we can see that the velocities in the vicinity of the PDO are completely different. Those are the exact simulation or the exact geometry of the numerical or experimental simulations, and here we are using this damping zone. So once we have done this, we can say that we have created this really fast methodology in which we can calculate, reducing 40% of the time, our experimental data. Now we can start playing with the dimensions of the dual chamber oscillating water column. We can change the width, the height, and so on, and we can try different or multiple configurations to achieve for the best solution. As we know, chamber 1 and chamber 2 works differently, so we can even play with different geometries. Once we have done, once we have done that, what we have done is added the porosity, the porous medium solver to the compressible interform in order to be able to solve what is some real experiments. So we need to add the porosity in order to replicate numerically this dissipative beach. It is important to realize that we don't care about, we know that the Forheimer equations are not perfect because they don't take into account the temperature, but this is just a dissipative beach. So they're just gonna be, let's say, eating the waves. And of course, sorry, I didn't hear.
Yeah, you can take millions of knots.
Okay. I'm gonna be working as well. And the last one is the PTO damping of a floating wake. So we're gonna be using some of the work that we have already validated before, the wave and currents, and the regular wave interaction with a wake. Starting from this work that we did before, now we're gonna define a wake which has a hollow cylinder of an outer diameter of 0.5 and an inner diameter of 0.25. And we are going to define a PTO which is going to be defined as a truncated cylinder here, and it's going to be placed inside the wake and filling it completely in the upper part. So we're going to be using the same numerical setup as we did it for validating the work by Palmetol. In this case, we are presenting the free decay of the Moody buoy when released from a given station in heave, and we have changed the porosity of the PTO from 1.0, which means there's no PTO. The air can flow through the PTO to 0.05, which means that the PTO almost is closed, so the water cannot flow inside. And as expected, we are having different oscillations with different periods because we are changing the physics of the device. Then we can impose for this oscillating for this wave energy converter, we can interact it with currents as we have done in the past. Here, I'm not exploring the mooring. I'm just plotting without the mooring, so we can see these things easily. Of course, when we create with higher currents, we're gonna have we can create here some hydraulic jumps. If we see from the top, we're gonna see how the PTO is following the displacement of the structure. And we can see that, of course, for bigger currents, we have bigger zones, bigger sawdust areas behind the structure. When, of course, if we go to the last time step, which is we just have simulated here 10 seconds, more or less we have achieved a steady state. And then we can add here the moonings to see that they are working properly. And finally, when we have used it with currents, of course, then we can use it with some regular waves.
Let's go to the conclusion.
So here we can see the displacement of the wake and the PTO, how, of course, they have the same displacement. And we can see here how the air is damped when passing through the PTO.
Let's go to the conclusion.
Yes, and that's all. Thank you very much for your attention. I'm open to questions.
Thank you. So there is time for a quick question. Yeah, please. I think that you have to come. I don't know how the microphone is just embedded. So please talk to the computer.
Thank you for the presentation, Mr.
Yep.
Yeah. And I have two questions. The first is that the parameter model, I have used your model and it runs really fast. But have you compared your model with other methods for modeling the parameter flow, such as the multi-phase method or other method?
So yeah, if I've understood, the question is if I have compared this median or this porous median model, the Forheimer equation, with other models, and the answer is no, not yet. So we have used this Forheimer model with plenty of projects related to coastal engineering, bring waters, and so on. The idea now is that once we have our model which is working, is to be able to change, because we know the Forheimer equation is not the most suitable one, for example, for modeling the PTO of this wave energy converter, but it's really straightforward to change those equations into other ones. We have found already some let's say formulas in the literature. The idea is to find some experimental data to be able to test it. But yes, our future plans, myself and Alessandro, is once we have this first paper, which is hope we will publish after summer, is to extend this work and to start analyzing different PTO models with the same configuration.
Okay, when you simulating the PTO, the floating WEC, the PTO of the floating WEC, do you face the problem of the uncertainty, the unstabilization of the simulation due to the PTO force?
No, we have not found any kind of instabilities caused by the PTO. It is true that we just have run those decay states, and we have run multiple simulations with currents and just several with regular waves. The idea as well is then to extend the work and to analyze, let's say, more energetic cases in which, of course, we're gonna have wave breaking and other kind of events that probably I would like to see how the OVERSET is gonna and the PTO as well, how they're gonna be working together with those cases.
Okay,
Thank you for the speaker again. And yeah, now we have a break